Hello guys, and welcome back to my YouTube channel or the Vig Structure Hub. This is a place where you learn, build and innovate. Today I want to tackle example number 1, and this is example of design of singly reinforced beam to BS8110. The question is on the board and it reads, a concrete beam carries a dead load of 150 kilonewton and imposed load of 50 kilonewton, has an effective span of 80 meters and supports 250 millimeter brick wall. Determine suitable dimension of the beam if grade 35 for concrete is to be used. So before you can begin tackling this question, I want you to be dividing your worksheet into 3 columns. So the first column, you will be quoting the tables you will be using in tackling such a question. And these tables are from BS8110. For example, as you can see here at the top, unless otherwise stated, all references are made from BS8110. So if you are using a certain table, then you have to write it here. For example, table 3.9, you will write table 3.9 from BS8110. And then this is where you will be doing your calculation. All of your calculation will be done here on the middle column. And then we have the output. The output is now the final design value. For example, if you are designing, for example, such a question, you have been told to determine the suitable dimension. So if your final B is 250, then you will say B is equal to 250. If D is 500, then you will say D is 500. If shear force is okay, then you say here shear force okay, and so on. So let's start tackling this question. Solution. So the first thing to do is to determine the loading. And you know that the formula for loading is the ultimate design load is equal to 1.4 GK plus 1.6 QK, whereby GK, which is the dead load, is equal to, for this case, it will be self weight of the beam, plus the dead load this beam is carrying, which is 150 kilonewton. So plus 150 kilonewton. And since you have not been given a value for the self weight of this beam, then we are going to assume a value which is so reasonable as a self weight of this beam. So assume self weight of the beam to be 25 kilonewton. So the dead load GK is equal to 25 plus 150. So this is in kilonewton. So it's equal to 175 kilonewton. So we go back to ultimate design load, which is 1.4. So ultimate design load is equal to 1.4 times GK which is 175, plus 1.6 times QK, which is imposed load. This is 50. So design load is equal to 325 kilonewton. 325 kilonewton. So 325 kilonewton, like that. So let's proceed. Allow me to clean here so that I can have more space for more calculation. So let's continue. So after calculating the design load, we now calculate the shear force. Now let's calculate the maximum shear force, which is capital V. Maximum which is capital V. So this one is given by W over 2. So our W is 325 kilonewton over 2. So this one will be 162.5 kilonewton. So you come and write it here. V is equal to 162.5 kilonewton. After doing so, distribute load along 6 meter effective span. Distribute load, which is 325 kilonewton along 6 meters effective span. So it means you take 325, which is equal to 325, you divide by 6. So you will get a loading per meter. So this one will be 54.17 kilonewton per meter. And then you come and write it here. Loading is equal to 54.17 kilonewton per meter. So you can draw your beam. So this is your beam. Let me draw. It is a simply supported beam. So that is the loading, which is 54.17 kilonewton per meter. And the span is 6 meters, like that. So from there, we can calculate the design ultimate moment, which is M. So M ultimate design ultimate moment, which is M, is equal to WL square over 8. So our W is 54.17 times 6 square over 8. So you will get 234.765 kilonewton meter. So you come and write it here. So M is equal to 234.765 kilonewton meter. After calculating our M, we now proceed to the question. The question asked us to determine the suitable dimension of the beam if grade 35 for concrete is to be used. So let's see how you want to determine the dimension of this beam. You will allow me to clear here so that I can get more space for more calculation. And also here, more space for more output. Yes, like that. So remember, we said that when you are designing a singly reinforced beam, beam, you have to consider this design should meet the following criteria. The first criteria is K must be less than or equal to K prime, and M must be less or equal to Mu, whereby K is equal to M over FCU BD square, and K prime is equal to Mu over FCU BD square. Also, M, we already have our M. Also, Mu is equal to 0.156 FCU BD square. So for a singly supposed beam, for a singly reinforced beam, it has to meet these two criteria, either this or this. But as you can see, for this case, we don't have Mu. There is no, we cannot calculate the value of Mu simply because we don't have D, but we have M. So we can use either of these two. K is less or equal to K prime, or M is less or equal to Mu. We can either use of the two to help us get the value of D. But since there is no value of Mu, but there is expression for Mu, then we are going to use this expression. So this is how we are going to use it. So we will say M is less or equal to Mu, but we already have our value of M. So our value of M is 234. 234.765 is equal to, no, is less or equal to Mu, which is 0.156 FCU BD square. We already have our FCU, our B and the D. Since this beam is supporting a brick wall of 250 millimeter, so beam supporting a brick wall of 250 millimeter. So in practice, it is good for a beam to match the dimension of the thickness of the wall. Therefore, the B of the beam is equal to 250 millimeter. So you will come here and say B is equal to 250 millimeter, like that, and FCU is equal to 35. This one, it is in the question. So we can use this expression to obtain D. So let's see how we can obtain D. So 234.765 is less or equal to 0.156 times FCU 35 times B to 50, then times D square. So we are looking for D. So you can ignore this sign and put equal sign. So it means 234.765 is equal to 0.156 times 35 times 250 times D square. So it means D square is equal to 234.765 times 10 raised to power 6. Why 10 raised to power 6? Because this was in kilonewton meter, and this is in Newton per millimeter square. Also, this is in millimeter. So we convert it to Newton millimeter so that we can have a uniform unit. Then we divide by 0.156 times 35 times 250, like that. So D square is equal to 20.8346. D alone is the square root of 20.846, which is equal to 456 millimeter. So that is our D. So that is our D. Now, after getting our D as 456, again, we are supposed to calculate the value of H. And before calculating the value of H, let's provide a nominal cover or the cover to this beam. So for mild, say, for mild condition, exposure, the cover is equal to 20 millimeter. So this one, you will get it in table 3.3 or 3.4 BS8110. So I will show you the table. So that is the table. So we have the simply supported, continuous, simply supported, and then we have continuous, and then you have beam, floor, and the column. So we take 20. So a cover of 20 millimeter. Then assume assume 8 millimeter diameter links, link and 16 millimeter diameter main bar. Like that. So since we were told to calculate the dimension, to determine the dimension, so we will assume any size of the bar. For link, you can assume 8 or 10, but for the main bar, assume 16 and above. Maybe 16, 25, and so on. So let's assume 16 millimeter for main bar. So now we are supposed to calculate the overall depth, which is h. So I want to draw a beam here. With this reinforcement bar. So this is how it will look like. So this is the link. Let me write it on the other side. So this is the link, and this one is the main bar. And this distance is what we call cover. which is 20 millimeter. So our distance D is from the top to the center of this So our distance D is from the top of this beam this is D, which is equal to our D was 456. So this is our D from the top of the beam to the center of this bus. So I want you to note something. So for a singly beam, we only design for tension. Therefore, the bar is provided on the bottom parts only. On bottom part only. But for the sake of structural importance, but for the sake of structural importance, we again provide top bars which hold the tension bar in place. So these are the top bars here. So this is the bar that has been designed for this beam, for a single beam. But this top bar is not designed bars. So these are a bar that is provided to hold these two bars in place. Because there is no way a link can connect only these two bars in place without top bars. So these top bars are just for holding the bottom bars. So you can provide any size. It can be even 10 or 8. But for the main bar, the size should be the one you have designed for. So like that. So H is this distance. So H is the overall distance of the beam. So how are we going to calculate this overall distance of the beam, which is H? So this is H. So remember our question asked us to determine the dimension of this beam. So the dimension of the beam, one is B and the other one is H. Remember, D is the distance from the top of the beam to the center of the tension bar at the bottom. So let me show you how we gonna calculate the distance H. So this H is equal to D plus, as you can see, plus a half of this main bar diameter. So plus a half of main bar, then plus diameter of the link, plus diameter of the link, then plus cover, like that. So H is equal to D is 456 plus main bar diameter is 16 over 2 plus the diameter of the link. The link is 8 plus cover. Cover is 20. So therefore H is equal to 492 millimeter. So H is equal to 492 millimeter. So round this into a reasonable figure. Say H is equal to 500 millimeter. So our H here is equal to 500 millimeter. That is our H. Now, after getting this H, we are also supposed to get a new value for D. So the new D will be 500 minus 500 minus cover, which is 20, minus, now we are going in a reverse way. So from here to here is 20, that is the cover, then a half of, then minus the link is 8, minus a half of this main, which is 16 over 2, we'll get 464 millimeters. So this is our new D, 464 millimeter. Now let's proceed to shear. We are done with H and D. So shear, so the formula for shear, so V, shear stress, is given by capital V over BD, which imply V is equal to the shear force is 162.5 times 10 raised to power 3 over B 250 times 464. This is our new D. Therefore, V is equal to 1.4 Newton per millimeter square. So remember, this V is limited to a maximum of 0.8 square root of 35. So for C35 concrete, maximum V allowed is equal to 0.8 FCU. So which is equal to 0.8 square root of 35. So this one is equal to 4.73 Newton per millimeter square. So therefore, 1.4 is less than 4.73 Newton per millimeter square. So, okay, shear okay. Shear okay. Deflection. So deflection is equal to basic span over effective depth. So which is equal to, the basic span is 600, no 6,000. So it was 6 meters, then you convert it to millimeter, you multiply by 1,000 over effective depth 464. So which is equal to 12.93 millimeter millimeter. So this one is okay because 12.93 is less than 20, therefore okay. So deflection okay. Deflection okay. So this 20 is obtained in table 3.9 of BS8110. So I will show you the table. So that is the table. As you can see, basic span over effective depth ratio for rectangular or flank beam, which is table 3.9 of BS8110. So we have the support condition, we have the cantilever, simply supported, which is 20. So it means this under should be less than 20 for the beam to be okay in deflection. So as you can see, the value given there is 20. So this is for rectangular section. So it is okay. It is okay. Now you can finalize the question by saying that a beam size of 250 by 500 millimeter deep will be suitable. A beam size, you can finalize by saying that a beam size of 250 by 500 millimeter will be suitable. And that marks the end of that question. So we meet again in my next session. Thank you for your time, and subscribe if you have not subscribed to the channel, and hit the notification bell so that you may be the first person to be notified when I upload a video. So thank you for your time. We meet again in my next session.